1C, we're going to look at stretches and compressions. So we're going to get stretches and compressions when we're multiplying a function, either the entire function, like we are on the left here, or multiplying just the input by a number. So the a value is what we're going to be multiplying these functions by. So that's just going to be any number in there for a, okay? So there's two different types. We can get a horizontal or a vertical stretch or compression. So the way you can tell which is which is by the placement of the a. So you notice on the left side of the page here, the a is outside the f of x. So multiplying the whole function by it, that gives us a vertical stretch or compression. Okay, so we can get two different types. I'll have to abbreviate here. So we could get a vertical stretch, or we could get a vertical compression. Okay, and the way you can tell if you're getting a stretch or compression just by looking at a function is the value of the a. So if the a value is greater than 1, that would give us a stretch. If the a value is less than 1, then that's going to give us a compression. Now technically, it's the absolute value of a in both of these cases that is greater or less than 1. So in other words, if we have a negative number, that's going to give us a reflection, which is not going to change the width of a v if we're looking at an absolute value function. So if you had, when we're saying absolute value of a is greater than 1, that means a could be something like 2 or 3 or 4, but it also could be -2 or -3 or -4. So it shouldn't be a number between 1 and -1 on the number line for this scenario. For this scenario, it is between 1 and -1 on the number line. Okay. All right. So let's look at this example here then. It says f of x equals absolute value of x minus 2 plus 3. And we're going to write g of x for a vertical stretch of f of x by a factor of 5. So the factor of 5, that just means the a value here is going to be 5, okay? So if we look at the format up above, it says a times f of x. So g of x, we're going to take a times f of x. A here is 5, so 5 times f of x, okay? And then I need to substitute in the value of f of x right here. So it's tempting to just put a 5 in front of the absolute value like this, but this is not quite correct because when we substitute, we want to do this, and that means we've got some distributing to do, like so. Okay, so we do want a 5 in front of the absolute value. It can't you can't distribute into an absolute value, so there will be a 5 here, but we also want to multiply the 3 by 5. So we'll have a plus 15 at the end, like so, and that's our new function after a vertical stretch by a factor of 5, okay? All right, so let's look at the horizontal side of things. So it gets a little confusing over here. So we've got our two types, which would be a horizontal stretch or a horizontal compression. The compressions are sometimes called shrinks. That's the same thing. So those are interchangeable. Okay. So you might think, oh, I'll just stick with stretch is going to be greater than 1. Well, it's flipped when we're on this side. So here a is less than 1, and for the compression, a is greater than 1 when we're looking at the horizontal side of things. And again, technically, that's the absolute value because the negatives just give us reflections and don't give us a stretch or a compression. Okay, so let's write g of x for a horizontal stretch of f of x by a factor of 3. Okay, so I'm going to do this the wrong way first because I see this all the time. It's totally understandable. You might think that, okay, I'm multiplying the input by a, and here a should be 3, so I've got f of 3x. I get it, but that's actually incorrect, and that's one of the reasons why this is confusing, okay? Because the a value on the horizontal side of things is not the same as the factor. On the horizontal side of things, you have to take the reciprocal of the factor. So if the factor is 3, the reciprocal of 3 is 1/3. Reciprocal means you flip the fraction upside down. So 3 over 1, flip that, you get 1/3. So my factor is going to be 1/3. So that means g of x is going to be f of 1/3 x. Okay? And now I have to find what f of 1/3 x is. That means I'm inputting 1/3 x. So where the input was, I'm going to change that to 1/3 x. And I'll have absolute value of 1/3 x plus 3 minus 7. There's no more simplifying I can do there. So the math side of it's pretty easy. You just replace the x with 1/3 x. The problem is that you have to remember which way to go. There's lots of junctions in the road where you could go left or right, and and you have to remember which is which. Okay. All right, so let's try a couple more examples. This next one is a vertical stretch, so that is important. It's vertical, so I'm on the left column here up above. And so if I zoom out a little bit, oh, I do have it on screen. It's a times f of x, and the a value is the same as the factor. So if the factor is 4, that means a is 4 on this example. Okay, so g of x is going to be 4 times f of x. Okay, then I'm going to distribute in all of this for f of x. And I got to remember that I'm going to need to do some distributing after I substitute. Okay, distribute the 4 right there and also down there. And so g of x then will equal 4 times absolute value of x plus 2 minus 20, not minus 5. Okay. All right, now let's try a horizontal compression by a factor of 3/5. So the factor is 3/5, but wait a second, that's not the a value. I need to take the reciprocal since I'm working in the horizontal side of things. So the reciprocal is 5/3, okay? And then I'm multiplying the input by 5/3, so it's going to be f of 5/3 x. Okay, so that means I'm replacing the input in this problem, which is where the x is. I'm just going to replace the x with 5/3 x. So I've got the absolute value of 5/3 x minus 1 plus 2. So that's what g of x is going to equal. Okay. Okay, this next one, we've got 2 different transformations, and the big piece of advice I have on this one is to do the 2 transformations in the order they're presented in the problem. So sometimes it won't actually make a difference, but especially when there's a reflection, you want to make sure you do them in the order. So I just always do them in order. So I've got a horizontal stretch, and then I'm going to translate 10 units down. So I'm going to do those bit by bit. Okay, so I'm starting with f of x. My final function is going to be g of x. So let me choose a different name for the function after the first transformation. So I'm doing my horizontal stretch here first. I'm going to have to write a little small. So I'll call this one h of x. So I'm going to take the original function, and we're on the horizontal side, so I'm going to want to multiply the input by something, but hang on. The factor is 8, so I need 1/8 as the a value. Okay, so I'm doing 1/8 x then. All right, so now I'm substituting 1/8 in for the input. Okay, so that means I'm going to have absolute value of 1/8 x minus 3, all plus 1. Okay, so if they only asked me for the horizontal stretch, I'd be finished. But now I've got to do the second part. I'm going to go 10 units down. Okay, so this is going to be my final answer after I do this one. So I'll call this one g of x. And here I'm going to take h of x, the last one that I wrote, and I'm going to subtract 10 from that. Okay, So here I'm going to want to substitute in h of x, which is all of this, into here. Okay, so that means g of x is going to equal absolute value of 1/8 x minus 3 plus 1. Still got the minus 10 out here. Okay, and this would look the same without parentheses. That means we just have to combine the 1 and the negative 10. And I've got absolute value of 1/8 x minus 3 minus 9. Okay. All right. Let's get to some graphing. Okay, on my next page, I've got these 3 lines graphed here already. Y equals x, and then I've got y equals 2x and y equals 1/2 x. So I just wanted to point out that when the coefficient in front of the x gets bigger, then my line gets steeper. Okay, and when the coefficient gets smaller, like with the 1/2 x, the green line, then it's going to get less steep. Okay, and that same kind of idea happens when we're looking at coefficients with absolute value functions. So I've got these 2's here, okay, in those 2 slots, and it doesn't really matter if it's inside the absolute value or outside. The same phenomenon is happening here. Compared to the parent graph, the v is going to look narrower when I've got a coefficient that's more than 1. If I have a coefficient that's less than 1, like the 1/2 in both these slots, then it's going to look wider. Okay, and that will come in handy, that idea. Those aren't technical terms, but they'll help to organize our thinking. Okay, so I'm going to look at the 4 types of stretches and compressions and get a little chart going here to organize things. Okay, so I've got the parent graph already drawn on all 4 of these graphs. So let's start with a horizontal stretch. So you might get a horizontal stretch with a function something like this. So we're on the inside that with our coefficient, that gives us a horizontal change. And the way I remember this, the horizontal changes are going to happen when the a value is touching the x. The x-axis is the horizontal axis, right? So if the 1/2 is touching the x, then you've got a horizontal change. If the 1/2 is on the outside of the absolute value, then it would be vertical. Okay, so it's based on the placement. Okay, so here the a value is 1/2. The factor, when we're doing horizontal changes, is going to be the reciprocal, so the factor here would be 2. Okay, so if I'm doing graphing y equals absolute value of 1/2 x, so this, what I already have graphed here is this, just to be clear about that. So now let's graph on the same graph. I'm going to graph absolute value of 1/2 x. So I'm doing a horizontal stretch. Okay, since my factor is 2, that means these 4 points, A, B, C, and D, are going to stretch horizontally. So they're going to go all out like this. They're all going to come out, okay? So the point C, I can see that it's 1 unit horizontally from the center of the graph. I want to double that horizontal distance since the factor is 2. I'm multiplying that horizontal distance by 2. So my new point C is going to look like that. That's C prime with the little apostrophe to show that's my new point C. And point D, I can see is 2 units horizontally from the center, so I want to double that, and that's going to put me out here. Okay, and then the same thing happens on the other side. So B prime would be here, it's just a mirror image, and A prime would be here. Okay, and then if I draw this in, so I've got a wider V by way of a horizontal stretch. Okay. All right, let's stick on the horizontal side of things. Let's look at a horizontal compression. So that's still going to be when the a value's inside the absolute value, but now you'd have an a value that's more than 1, like 2, Okay, so a is 2 here, but the factor would be 1/2. Okay, and still these points, just like on the last one, are moving horizontally. So I'm looking at these horizontal distances, but here since the factor is 1/2, that means I'm going to multiply those by 1/2. That's the same as dividing by 2. So if you look at point D, it's 2 units away horizontally from the center. So I want my new point D to be 1 unit away. And point C, I take half of that, half of 1 unit would be right there. Whoops, it disappeared. Okay, and the same thing on the other side. So this one, I know this one is going to be narrower because I've got a number that's more than 1, and I do get a narrower V by way of a horizontal compression. These points, in other words, are moving in horizontally, like so. Okay. All right. Next one, we've got a vertical change. So that's going to happen when the A value is outside the absolute value. And we'd get a vertical stretch when we've got something like 2 or 3 or 4. All right, here the A value is 2, and that's also the factor. So you don't take the reciprocal for the vertical changes, okay? So here I'll write in the equation for the next one. This would be maybe when I have a 1/2 out here. And that means both my A value and my factor are 1/2. Okay, so let's look at these vertical changes then. So that now I'm looking at these vertical distances, and since it's a stretch, those points are all going to move away. They're all gonna move up, away from the vertex. The vertex stays put, but all the other points are gonna move away from the vertex vertically. And since the factor is 2, I'm doubling the height of these points. So point C is 1 unit above the vertex. I want to double that. So there's my new point C. So a lot of times I'll see people say, oh, I put the new C 1 unit above the old C, so I'll move point D 1 unit up. But we're doubling that height. So D is at a height of 2 units. So I want to double that. Now it's at a height of 4 units. Okay, I'm not going to label all those points, but that's my new A, B, and C, and D. So I've got a narrower, I know this is narrower because it's a number more than 1, but this time it's by way of a vertical stretch. Okay, and it might seem like, hey, a vertical stretch looks the same as a horizontal compression. And they do look the same for these type of graphs, but the points have moved in a different way. And that's important because if you had an S curve, which, you know, that's what a sine curve looks like, which we'll get to later in the book, it's going to make a big difference. It will not look the same if it's a vertical stretch or a horizontal compression. So it is important to understand which way these points are moving, okay? Here I'm looking at the vertical distances, but this time I'm taking half of the vertical distances. This one should get wider. So if I move, I'm taking half of those heights of those points. I don't know why it always keeps erasing like that. All right. When I take half of the heights, then I've got you can think of it, I've got a V that's half as tall. I guess that's, or it's twice as wide if you want to think about it like that. Okay, so there's a little chart that might be helpful to get started on graphing problems. All right, so let's try actually graphing one from scratch then. All right, so my advice on problems like this is to find and plot the vertex first. You won't have to move the vertex if you get it in the right place with the method I use. Even if there's a reflection, it won't move, okay? So let's start with that. So looking at this example down here for the x-coordinate, a lot of people look at this and say, oh, the vertex is -3, -2, because they just changed the sign of the 3, but that's incorrect. That's not quite right, okay? I want to take the contents of the absolute value and set that equal to 0. So the 1/2 is going to play a role here then, okay? So I'll subtract 3 from both sides. And now I want to double the equation, because if I do that, 2 times 1/2 is 1. And so then my x value is -6, okay? The y value is -2, so the actual vertex is going to be -6, -2, not -3, -2. Okay, so let's go ahead and plot that. -6, -2 is right here. Okay, my next step is going to be to plot what I call the ghost points. So I'll just say lightly graph the ghost. So that's, if you're using a pencil, lightly graph it without, and that means I'm doing this without stretches or compressions. So this does have a stretch or compression, but I'm just going to pretend it doesn't for the ghost. Okay, but include any reflections. So that means I'm just looking for, does this open up or down is all I need to worry about. So there's no negative in this one in front of the absolute value there. So it doesn't open downwards, it opens upwards. So here's my ghost points, and here I'll do this, I'll do my ghost in red. So if I go up one to the right one, up one to the right one, same to the left, and I'll just do this lightly then, and I'll do a dashed line. That's what I'm going to call my ghost curve, or my ghost V. So that's with no stretch or compression. But now we are going to do a stretch or compression. So now I'm going to have to start analyzing the 1/2, okay? So this is the hardest part of it. So the first thing I like to think, well, is this going to be a wider V or a narrower V? So this one, since this is a number less than 1, I know it's going to be wider, okay? The next thing I want to think is, well, is this going to be a horizontal change or a vertical change? And for this one, my absolute value bars got obscured here, but one was there and the other was there. So I'm looking for the 1/2. Is that inside touching the X or not? It is touching the X. That means this is a horizontal change. Okay? And so it's either a horizontal stretch or compression, and to figure that out, I need to put wider and horizontal together. I need to think of these as a pair, okay? So let's think about it. Moving horizontally, that means these points can only move left or right. So they're either going to move out or they're going to move in. Okay, so let's imagine they're moving in. So I'm going to move like the top points in a unit. So if I did that, I'd end up with something like that, which is narrower. It looks narrower than the ghost, right? So I'm going to have to move these out, because if I move them out, then I will get a wider V. And that's a conceptual thing that some people can see very easily and other people have trouble with, but I'm just trying to describe this the best I can. So yeah, if we move these points out horizontally, so since the factor would be 2, right, the reciprocal of 1/2, that means I'm doubling the horizontal distance. So I'm taking this 1 unit from the center and doubling it. I'm taking this 2 units from the center and doubling that. And then I can see, all right, this is going to give me a wider V, right? So that means this is a horizontal stretch. Those points are stretching horizontally away from the middle of the graph, okay? All right, and then we can draw our final V in here like so. Okay, you need to put the arrows on both ends to show it goes on forever. A lot of times I have people just draw a V and it stops at the points, but you need to show that it stretches infinitely in both directions. Okay, let's try another. So I'm going to start here by finding the vertex. There's my x-coordinate. Here's my y-coordinate. So the vertex is -2, -1. -2, -1. Then I'm thinking, does it open up or down? Well, there's no negative in front of the absolute value, so that means it's going to open up. So now I'm going to put in my ghost points. Okay. And I got to figure out now what I'm going to do with those ghost points. I'm going to stretch them either horizontally or vertically. So let's think about the 3. That's what's going to cause the stretch or compression. So first I'm thinking wider or narrower. Well, that's a number more than 1, so it's going to get narrow. Okay, and then I'm thinking horizontal or vertical. Well, this one isn't touching the x on the inside. That means it's going to be a vertical change. Okay, so I'm moving these points just up or down. So they can only move either up or down. So either these points are all going to stretch up, or these are all going to go down towards the vertex, one or the other, okay? So let's think about which way would give us a narrower V. Well, if I brought them down something like this, then my V would get wider, right? It would look wider like that. So let's try pulling them up. And if we're pulling them up, that means that's going to give us a vertical stretch, okay? So here, here I'm not doubling the height of these points. I'm actually going to triple these heights because my A value here is 3, right? So I'm looking at those heights that I just highlighted. So the ones closest to the vertex are 1 unit above. If I triple that, I'm going to make these 3 units above the vertex. So 1, 2, 3. Not 3 units above the point, but 3 units above the vertex. So there's that first set. And the outside points are 2 units above. If I double that, triple that, sorry, it's 6. So I want these to be 6 units above the vertex, which puts me at the very top of the provided graph here. And then I've got a narrower V by way of a vertical stretch. All right, that is the end of the section, and I will see you next time.